watching Henry AI Labs podcast. This is the first episode of a new series where I'm going to be talking with experts in deep learning and artificial intelligence about different papers and interesting areas of deep learning. Today I'm here with Edward Dixon, a data scientist at Intel.
I'm Edward Dixon. I'm a data scientist at Intel. I've been applying machine learning in a few different problem areas like NLP, machine vision, audio classification, structured data problems. My day job is slightly less hands-on. I'm working to help larger companies and governments to make more effective use of machine learning, especially deep learning. I do get to collaborate with some really interesting companies in the machine learning area like H2O and Selden, make it easier for people to get machine learning into production. Away from the day job, I do slightly more technical things, volunteering with a nonprofit called Thorn. It was founded by Ashton Kutcher and Demi Moore to fight child sexual exploitation on the internet. That involves using machine learning to help investigators to cope a bit better with really a huge flood of data, right? We're talking lots and lots of videos and images that they need to process. And I'm also working on a book with some co-authors. It's called Demystifying AI for the Enterprise, and it'll be published by Taylor and Francis later this year. So shameless plug there. That's not really so much for the people listening to this podcast, but it might be for their bosses or their future bosses. So at the moment, a lot of senior managers are aware of AI, they're aware of machine learning in a general sense, and they're excited about the potential. But if you're not already working in the field, how do you actually identify some use cases for your business, and how do you build a team and start building and shipping a product? This book is for those people, so they can start those projects and get some money and hire all of our audience to build the cool new stuff.
Thank you very much, Connor. It's really, really great to be invited. I've come to know you on Twitter. I've read the articles. I've watched the videos. So it's great to be finally in the virtual studio with you.
Yeah. So today we're talking about a paper, stochastic weight averaging, which is a really interesting idea, sort of related to ensembling deep neural networks. And this has been really interesting to me to study. I first saw ensembling deep neural networks with the architecture called Hydra, where they train a bunch of separate feature extractors and then combine them later on to form the predictions. So I just wanted to know your thoughts on ensembling deep neural networks, and if you think, because I know in traditional machine learning it's been really successful.
So when I've used ensembles of models, it's never been deep neural networks, and a big part of that has simply been to ensemble deep neural networks. You've got to train a lot of deep neural networks,
right?
And usually just training one is taking a long time. But actually, it's worse than that. If you want to put it into production, then you're talking about putting an ensemble of networks into production, and that's a big bulky thing. If you want to use, let's say, 10 models, that's a lot. So where you might be used to using ensembling and ensembles of trees and decision trees, where they're basically practically free, so nobody worries about it. People think differently about the deep neural networks. So I thought that it sounded like a good idea, but I didn't actually bother trying to do it myself. So that was what caught my eye with this paper. It's like, one way of looking at it is, here's a way of doing ensembles where there's only one model. It's like on the cheapest possible ensembling, right? You've only got one model, but you end up with the same results that you might have got if you had trained quite a few models. That's the very, very beautiful thing about it.
Well, so one detail of the paper I wanted to clarify and talk about is, so when they do the stochastic weight averaging, it seems like they train a bunch of different models and then they just average the weights together after training. And I was curious if this is still like a semantic operation to just average the weights together after doing the training.
Right. So I think one of the key things in the paper is exactly how the averaging works. So the authors point out that people had previously had this idea that, okay, when we're doing stochastic gradient descent, we know that our parameter updates are noisy. Right, that's built in. It's stochastic gradient descent. We use small batches, but we still get to a pretty good solution. But wouldn't it be better if we did averaging? Everybody knows when you're drawing samples, if you do some averaging, things work out better, right? Basic statistics. The only thing was, when people did it, it didn't work, right? If you averaged the weights and then trained them up, if you took the weights at a given time and you trained a bit more, and then you averaged the weights, that didn't help. The averaging wasn't giving you the benefits that it should have, and it was not obvious why that was so, right? When I talked to a statistician, and it was obvious to her, I said, hey, there's this great new paper. They're talking about how averaging didn't work when you're training deep neural networks, and they figured out why. And she said, yeah, well, it's because the errors were correlated, right? I said, yes. Yeah, the points effectively with stochastic gradient descent and averaging. I think what the paper says is that in previous work, you were taking your weights at different points in time as you trained, and then you were averaging them, or maybe you would do maybe some kind of exponentially weighted decay, and you're averaging as you go along, so it doesn't cost you too much in memory. But you're not really averaging all that well because you're sort of approaching this minima area, right? You're approaching this valley, and the things that you're averaging, they're basically from one side of this valley. And so the averaging you're doing is pulling around weight space a bit, but you're not really moving through the lost surface the way you'd like to. You'd like to get deeper into this flat valley floor if you could. But averaging that way isn't, because you're just basically wandering around one side of the valley, averaging your positions, and when you've done all that, you're still on one side of the valley, and you haven't moved into this broad, flat, safe region of parameter space. That's the other thing about this paper, right? The ideas seem very clear and intuitive, and seem to be well illustrated.
Well, one idea that I was interested in is sort of like you discuss how the errors are correlated, but I seem to like understand it as the initialization. If you have this like loss service that's like super hilly with all sorts of local minima and one global minima somewhere, but it's a really odd shaped surface. But the way I see it is the different initialization points put you on very different starting points. So I don't necessarily think of it as the errors being correlated. That was one thing that I was sort of unclear on, because I think the different initializations result in completely different errors.
So they would. The trouble was that what previous people were doing was, right, they were training one model with stochastic gradient descent. So they're walking down, they had that random initialization. So you're somewhere on a hill somewhere, and you walk down to the valley, and then when you find the valley, you keep track of your position, your previous positions, and you average them. But you've been walking along one side of the valley, and that doesn't really move you anywhere. But my understanding is that with this paper, what's happened is you do the normal training. You can use a pre-trained model that's been trained with normal SGD. But now when you're on the valley floor, where normally you would have dialed down your learning rate a lot, right, to avoid oscillating, they say oscillation is what you want, right? We want you to run around that valley at crazy speeds and wildly overshoot, and hit the valley wall on the far side. That's fantastic, because that's going to give you're going to explore more. And I think I say in the paper, you're maximizing exploration. And yes, the individual places that you visit, they're not going to be quite as good as the positions you visited when you were doing a very cautious SGD with your very cautious learning rate. But that doesn't matter, because when you average them, you've been pinging off the walls of this valley in all directions. And when you average all these crazy places you visited, the average is going to be the centroid of this valley. And that's really good, because you've got lots of flat land around you. And that's super important, because they show some pictures of the error surface. This should really be in the video. And they show the test error surface and the training error surface. And they're not the same. They have a big overlap, but they're not the same. So you really want to be in the middle of that valley and not at the edges. The middle isn't that much better, but it's more reliable. If you're in the middle of the valley for the training set, you've got a good chance of being in the middle of of being somewhere deep in the valley for the test set also.
So with respect to talking about the neural loss surface, do you think it's important to, like, I know the paper discusses if you have these sharp minima rather than like a wide minima, that it's going to be a symptom of overfitting, and a training loss surface with these very sharp valleys aren't going to generalize compared to having a wide training set valley. So do you think that you should, like look at, is there some way of inspecting the training data to see if it has this kind of shape before you train your model? And if you find this kind of characteristic, do you think that means that you should be focused on the data engineering portion rather than trying a stochastic weight averaging or some kind of clever trick around this potentially like end all be all problem with your data set?
So I haven't thought about this at all. So this is totally off the cuff, but I'd be happy to bet $100 that any data set you try is going that with any data set and however you initialize your model, you're going to find these sharp kind of cliffy parts in your error surface. I'd be surprised. I'd be very surprised if you could be sure that there were none there before you start training. Put it that way, because like you've got to remember, like this manifold, we're kind of pushing it into being using we're kind of pressing it into being using our loss function, and we've got this really high dimensional, we're working in a really high dimensional space. It's that we already know is not convex. I find it hard to imagine a way to guarantee that the landscape is going to have this friendly, gently curving surface. Like obviously normalizing helps, and we do that already. Yeah, I'd be surprised if you could do much better than normalizing. I hope we're all normalizing already.
Yeah. Would you mind explaining really quickly what you mean by normalizing the loss surface?
Yeah. So there's this. So early on in machine learning courses, hopefully you come across the idea that when you're training a simple model, right? So let's say logistic regression, you've got this nice convex loss surface, right? So it's a bowl shape. But the problem is that if you don't normalize your inputs, the loss bowl may not be circular. It may be very, very elongated. Right? Now that sounds harmless enough, right? It's still convex. It's still got a minima. There's still a single global minima that you're going to get to. Mm-hmm. But the thing is, if it's very stretched out on one axis, that means that your learning rate that's suitable for the long, slow axis, where you've got a very gradual gradient, is going to be very unsuitable for the short axis. So on the short axis, it's going to have a steeper gradient. You're going to want to move down slowly and carefully so you don't overshoot the bottom. Mm-hmm. And then the long axis of your ellipsoidal bowl, a slower learning rate is going to kill you. Right? You're going to be walking along this nearly flat plane practically forever. But if you do this really simple thing, if you scale your inputs, right, so that you have unit variance for all of them and they're centered on zero, then your loss surface has this nice, it becomes circular, right? You still got to walk the way down to the center, but the gradients are going to be similar in all directions, and you're not going to have this problem of, you will find, so when you train, you'll find that your model converges much more quickly. It might even converge at all, actually, to be honest, if you don't normalize. And I know this because I've done this the wrong way. And having done it the wrong way and realized eventually I didn't normalize the images going to a model, I never again forgot.
Yeah, I guess I never thought of normalization with respect to the loss surface. I always thought it was just a way, like thinking about like batch normalization, where you keep the gamma beta parameters to sort of maintain a normal distributed set of features at each layer. I always thought that this was just for the magnitude to keep the magnitude of the gradient from being too different in different layers, to sort of have like a consistency to it. I guess with normalization, I never really have thought about how it reflects on the loss surface. So I'm curious, like the difference between scaling, where you just subtract the maximum and then divide by the average, or something, or subtract the average, divide by the average, something like that, compared to a normal distribution normalization. Like I'm curious what these two different, because I know the two common. It's like you can scale the features down so they all have like a 0 to 1. They lie between 0 and 1, or they can take on this like normal distribution of values. So I'm curious, like, what do you think how that relates to the loss surface?
Oh, so I mean, it doesn't. So first of all, you don't have to be super careful with when you normalize. It's okay to be a bit sloppy because it doesn't make too much difference in practice. Your loss surface, your loss surface is going to be a complicated surface anyway.
Yeah.
Right. Unfortunately, that's why we need the gradient descent to find a way around. Yeah, don't worry too much about it. Just try to make sure your data has the same scale on all the axes, and that mean centering as well helps a bit. Although the bias should be easy enough to learn. Yeah, I don't think I ever experimented with not centering the data. Also, it probably has quite a low cost. I guess you'd learn the bias very quickly. But still, just normalize everybody. It's a good practice. So that's why. So when I heard about batch normalization, I was already used to normalize my inputs, and that batch normalization came along. I was like, well, of course. We were all mad. Yeah.
Well, so do you have an intuition on why batch normalization normalizes it in the in the mean variance type of way compared to just scaling the features down to lie between a similar interval at each layer?
No, I don't, and I'm not even sure. No, I don't. That's the answer. I can introduce you to a guy who would introduce the guy to Sergey Yoff, one of the authors, and then you should ask him.
Oh, that would be great.
That's what I can do. I have Sergey Yoff's email address actually. Yeah, talk to Sergey. Ask him.
Okay. So returning back to the general topic of ensembling deep neural networks, do you think I've seen a lot of interesting things on data compression? I mean, on model compression, especially the ones that are optimized for running on the phones and in embedded systems. Do you think that an ensemble of small mobile optimized networks that are ensembled would perform better than one monolithic network? Say a 400 megabyte ResNet 200 compared to maybe 10 ensembled of these MNAS nets that the Quack-Lee lab is developing?
That's an interesting question. I hadn't thought. So, I think that a few days ago I would have, before I read this paper, I said, "Oh no, I think the big model is just going to be better." But now having read this paper and thinking about how you're basically, they say that basically with your stochastic gradient descent, you're getting back into the paper. So I think that the small models actually might be more competitive than I would have previously thought, and the reason is this. They cite, the authors here in the SWA paper cite previous research that says that you can interpret points proposed by SGD as being constrained to the surface of a sphere, since they come from a high-dimensional Gaussian distribution.
Okay.
So that's a bit of a mouthful right there, but basically, if you pick one number from a Gaussian distribution, right, it might be close to, we'll assume it's mean-centered, it might be close to 0 or it might not. But if you're picking a vector, right, a vector has lots of components, it's not likely that all of the components will turn out to be 0 at the same time. And if you have a vector that has enough dimensions, nearly all the vectors that you pick, they're going to have similar norms, and so they'll end up coming from basically the surface of a slightly fuzzy sphere. Just before our call, I did a quick notebook on Google Colab. By the time my vectors had 10,000 dimensions, all their norms were between, and they had a variance of 1, I think. All the norms were between 98 and 102.
And this is from the different initializations that it trains it on?
So you'd have to read a paper, Mand et al. 2017, but they say that under certain simplifications, you can understand SGD is basically ending up somewhere on the surface of this fuzzy ball, and that SWA averaging is what lets you get inside that ball. Right. So if SWA is working well because it lets you get inside that norm ball, well, if you train lots of models, initializing them from different random initializations, you'd expect to approach that surface from different directions. I'd say they might be in with a fighting chance. I wouldn't be. Yeah, I actually wouldn't. So that's one where I wouldn't be placing a bet, and I'd be giving even odds that somebody could do an ensemble of small models and do better than one large model. That sounds possible. Saying that, if I was trying to do that, I probably would modify the way I train the small models, right? If I was trying to win that bet, I'd probably use model distillation. So rather than train my small models directly on the labels, I'd train my humongous model first, and then I would train my very small models on the output vectors from the very big model.
And then they would have still some kind of variation in them from their own initializations,
so what would happen
right?
is they still have the random initialization, right?
Mm-hmm.
But they have some more information about the problem. So the very large model, instead of giving hard labels like this is a dog or this is a cat, right? You've got soft labels in the large model where, maybe there's some cat that's a little bit doggish, or maybe there's a dog breed somewhere that's a little bit cattish, right? And maybe the labels come out, it's dog with probability 0.95, but 0.04 it could be a cat. And that those labels, the intuition with model distillation is that those softer labels give information about the underlying structure of the data that allows the student model, the second model you train, to learn much more efficiently. And I've done a little empirical work on that. I wrote a fun little article about how to pirate a model as a service, right? So if you see a cloud service where you put in some data and a model outputs some values for you, instead of paying to use the API, you can just put a few thousand samples through, and you'll already be able to train your own model that's about as good.
Well, that's interesting as well. So you could use the full training set to train the parent model, and then when you're distilling the information down, you could use less labeled data to do the distillation.
Oh, absolutely. And so once you got the big model, right, it's labeling data for you. Obviously, it can't. There are limits to generalization. But so this student teacher, so it's called student teacher training or model distillation. Like there are a few ways you can use it. One way is to make a small model out of a big model. When I say small, you might be able to get similar performance from 1 or 2 orders of magnitude fewer parameters. So yeah, if I'm trying to do your thing of getting an ensemble of tiny networks, I'd start with a very big network. I'd use my student teacher model distillation. I'm still able to take advantage of random initialization, so that's good. And then I can do my ensembling afterwards. I'd be interested to see a horse race there between SWA and straight ensembling. You might have a paper there.
Yeah, go ahead with my advisor after this. But
so coming back to the paper, actually, there's 1 or 2 more things there that I thought were pretty exciting. Like you were mentioning hardware there. So one thing about hardware is that we already know that we can get away with quantized weights for inference. Right? People can do inference very successfully 8 bits. I work at Intel. We're very excited about 8-bit inference. It seems to work about as well as doing inference with proper floating point numbers, and that seems to be truer the bigger the model. So it's very nearly true for ResNet 50. By the time you get to Inception v3, you just can't. I can't seem to. My experiments, I can't tell the difference, right, with the quantized model. But the thing is, you're quantizing the model after you trained it, right? So we're training a model with these 32-bit parameters, say. We all know that's nonsense because, like, we know that the exact values of the parameters in neural networks are not super important, right? There's lots of empirical work to show that you don't really need those many bits of precision, but at the same time, if you've got very noisy gradients, the model doesn't converge. Okay. So after you've trained the model, you can throw away lots of precision. And if I go back to student-teacher training for a moment, when you go get those soft labels from your teacher model, I mean, you can quantize those soft labels very severely, and they'll still be very informative. Like you can basically quantize them to 1 decimal place, and they'll still be super effective for the student. But going back to the model quantization, it turns out that if you use stochastic weight averaging, you can actually train a model using 8-bit weights. So if you think about that from a hardware perspective, right, an area of silicon that before was dedicated to 32-bit weights, to 1 32-bit weight, now it can be used for 4 8-bit weights.
That seems really interesting. I just had one quick clarification. When they quantize the weight, does that just refer to Like if you have a 32-bit float, you would just truncate the values so that it only fits in 8 bits, or is there like a more sophisticated scheme to doing that?
So for model quantization, at the moment, if you're, a lot of companies that aren't Intel and Intel as well have tools that will let you take a model with 32-bit weights and then quantize it. You'll often need to run a little bit of data through the model to help it get the ranges right for the quantization. There's a quantization procedure. There's a few variations. So there's public work there. I need to be careful what I say though, because I could accidentally talk about something that's not public. But effectively, there are procedures that will take a 32-bit model and give you a model with 8-bit weights that does about the same job. It's a little bit more complicated than just throwing away bits of precision.
All right.
But not a lot more complicated. But with a paper that follows on from this paper, though, the SWA paper, they are, and a lot of the same authors I think are on the paper, they're able to train a model using 8-bit weights during training. So that's a big deal. I mean, 8-bit weights, first of all, obviously they're smaller, there's less memory. That could be good if you're working with LSTMs. Memory's always a bit of a headache with the LSTMs. But then there's also less multiplications. So obviously you might just do 4 times as many multiplications and throw in more weights there. But it could be good at inference time, right? So latest generation of Intel processors, Cascade Lake, you've got VNNI, vectorized neural network instruction sets where you're doing vector-vector multiplication with 8-bit weights in those vectors, 8-bit components. So that's the thing. We've got a paper here that gives you models that are a bit more accurate, but they also generalize better. So that's a good thing. It gives you a path to training at lower precision. That's also a very, very good thing.
Yeah.
And there's actually another research avenue that it opens up. I'm not sure how closely you, our listeners, have been following Bayesian machine learning or Bayesian deep learning.
A little bit. I've heard that Bayesian deep learning and the uncertainty estimates work really well with correlation to the model compression techniques.
Yeah, so it's like everybody's very excited. So it sounds great. It's just that you don't see a lot of people actually using it, because usually when you look into Bayesian techniques, they usually turn out to be really expensive. If you're trying to work with deep neural networks, usually it turns out there's some huge cost once you get to really big models, and it just turns out to be infeasible. But as with the Bayesian neural network, I'm possibly going to over-explain for you, but just for the benefit of the listeners, what you'd really like to have is, instead of just having model weights, you'd ideally like to have a distribution for each weight. So instead of saying the weight is X, you want to be able to say, okay, I think this weight has a value of X, but it could be plus or minus. It could be plus or minus. It's X plus or minus Y. I've got a little Gaussian distribution going on for each parameter. And if I have a distribution over all the weights in the model, that'll let me do a really cool thing. That'll let me give really well justified uncertainty estimates for the model outputs. Right? So I know we have class probabilities right now, but those don't always line up 100% with reality when you read it closely. And there are a lot of real world applications where knowing how uncertain your model is super, super important. So I work at Intel, but in the introduction, one of the things that I skipped is that I also volunteer at Thorn. I worked a little bit with Interpol's DevOps group, and a little bit with NECMEC. In all those cases, we're using machine learning to help with basically anti-child exploitation use cases. That essentially has to do with using biometrics to recover children that are being sexually abused, or to find their abusers, which usually comes to the same thing. And when you're working in that area, knowing model uncertainty can be really useful. One of the things I'm working on is age estimation. How old is a person in an image? If you're trying to deal with a huge flood of images, or really like a very, very large number of images that you can't review with a human, you're going to have to prioritize. And one way you might be doing that is by looking for images that you're very sure feature younger people. And so that sounds like a regression problem. Focus on the most young-looking pictures first. But I used to do regression with much simpler models, like a long time before I heard of deep learning, in industrial vision settings. And in industrial vision, they're super keen on having error bars on your estimates. right? It helps people to keep their arms and legs when they're working, attach them when they're working near a welding robot. Say you want to have really good error bars on your machine vision rated stuff in that particular domain. But the same in this domain, right? If you're prioritizing, in case you want to prioritize the younger people, you want to prioritize not just the younger people, but the people that you're very sure are young, right? If you think somebody is 14 plus or minus 10 years, that's not as useful as somebody I think they're 14 plus or minus 3 years, right? You've got to make the best use of your investigator's time. But when I was working in industrial machine vision, I was working with very simple models where it was very easy to get uncertainty estimates. We could use just some error propagation math and very straightforward techniques to have very, very good error bars. Can't do the same thing with a deep neural network, but I'd like to, and I've been looking for a way to do that. And I read through this paper, and I find out that actually there are applications to this paper. So there's some follow-on work called SWAG, G for Gaussian, where they say, right, we've been averaging models, right? Averaging model weights. So we've been estimating a mean for all of our weights. Why don't we also estimate a variance? Right? Because we're already doing all the work we need to do that, to get the variance of the weights.
Well, so wouldn't you need some additional memory to define a distribution of the weights?
So you would, but the good news is that if in the original SWA paper, they address the concerns of memory and say, look, when you're treating a deep neural network, obviously we're storing a second copy of the weights to the averaging of the average that we're keeping. So that sounds like we're doubling, but actually most of your memory budget is going on the activations of weights rather than the weights themselves. So our technique only costs you an additional 10% of memory.
The activations of weights, could you explain that a little more? How does that?
So when you're training a deep neural network, so just for the audience there, so when you're training a deep neural network and you're doing your back propagation and so on, when you're doing your forward pass, right, you're needing to record how much the weights affected the outcomes and then work backwards, like an assign, credit, and blame through your model. And there's a lot of bookkeeping of numbers that you need to do that, and that all costs memory. So
okay.
So you might have your model weights might cost you X megabytes, but it turns out you end up using 10x megabytes by the time you're during training. Now during inference, then your memory requirements are much more modest. So it turns out that storing an extra copy of the weights, as you need to do for SWA, is pretty cheap. Right, it only increases your memory budget by about 10%-ish. So that's not too bad, especially because you're effectively getting the benefit of ensemble. It's like, instead of spending 10x the memory, you can spend, 100, just 10% more. So then if you want to calculate the variance of the model weights as well as you go along, then that's a similar increase, right? So you end up spending, let's say 20, 30% more memory than you otherwise would have. But you don't really end up, and you end up with a little bit more compute, but not much. Again, it's a similar increase. It's an increase, but it's not it's not an order of magnitude increase. And what you end up then when you're finished training is you've got a model. Now there's not just like an ensemble of models, but also you have uncertainties for all of the weights, and that lets you sample the model, right? So it's Monte Carlo that lets you draw a set of weights from this distribution. Do inference with that set, and then you draw a set of weights. And so with the SWAG, you end up being able to do two things that sound really useful to me. You end up being able to get better uncertainty estimates for your predictions. So that's really important if you're trying to industrialize machine learning, put it out there into the world, as I hope we're all trying to do.
Yeah.
But there's another thing that it does that's very nice. So we collect training sets and we do our best to make the training set representative. But in the real world, when you deploy an application, samples come in that you just people sample areas of the input space that you didn't think about, and then your model is not going to work very well. And so you basically people are giving you inputs that are out of distribution, right? They're not drawn from the training distribution. It would be really nice to detect that. And one of I guess we're moving on. This is really a follow-on paper rather than this specific paper, but one of the great benefits of SWAG is that it seems to do a better job of telling you that a given sample is out of distribution. It doesn't come from the trained distribution. And and if that's the case, then you can flag that to users and say, okay, look, this isn't this kind of stuff I'm familiar with. I'm a car that learned to drive in Southern California, and your rainy Irish roads, they're so narrow, they're so damp. I have no idea what to do. Maybe this is the middle of the road, maybe it's not. Who knows? So I think that's a pretty interesting direction, right? Because traditionally, doing that kind of thing was very expensive, and with their paper, they're doing it, nearly for free, right? It costs a little bit more, but not much more. Right? You're barely going to notice the extra memory and computational cost. So it's one paper, but it's basically got, I think, something for everybody in it. It gives you, I think it gave me a better intuition for the dynamics of machine learning and a better geometric understanding of the loss surface and what's and how SGD interacts with the loss surface. I think I understand that better. And then it also gave me some interesting directions, right? So, training with 8-bit weights, that's pretty interesting for Intel. That would play really nicely with some of our hardware, some of our new hardware. So that's great for some things I'm working on for nonprofits. Uncertainty estimates, that's great. More robust models, that's also great. I don't think we talked about semi-supervised training. There are some great results in this paper as well about that. I don't know about you and the datasets you're working with, but I'm somewhat data constrained. I'm working on age estimation at the moment. I've got a high quality data set that maps faces to ages it's got about 7,000 samples. Right, so it's not so small that you're laughing at me that you're not going to get anywhere. Yeah. But it's not overwhelmingly large, right? It's not ImageNet. So I have a path to getting to maybe maybe 30, 40, 50,000 samples with good labels, but I don't expect to get to millions. So any paper that talks about semi-supervised learning and has impressive numbers, I'm very excited about that.
Yeah, that's great. I'll keep you in mind if I ever come across something. I have seen some work with the JFT 300 million data set that they are making progress with that, but I'm not sure how that would translate to age estimation.
Sorry, can you talk more about that?
I'm not super strong on it, but I just know from a high level that there's been some new work very recently on unsupervised feature extraction. And maybe you could do that unsupervised feature extraction and then fine tune it with your data set. So some kind of like pre-training type of scheme with the unsupervised features. But I'm not sure if it would.
Yeah, I that's an avenue I definitely. So I've got a pass of. I've got two sort of data harvesting and cleanup tasks to do, and after that, my next avenue then is going to have to be fancy data augmentation. So I'm deliberately not doing that right now because it would distract me, and I know I have a path to getting some really high quality data, so I need to do that. And I've got a path to I've already got a very large noisy data set that I need to fully exploit. But there's a really cool paper called it's called VAE.
I was reading that just before this actually. Very interesting.
Right. So
yeah.
Vignal's one of the authors. So that's
right.
This is where video is great. I mean, they're able to generate highly realistic images of faces, but also images of things from ImageNet classes. The images are much more coherent than the images we've seen before. And the thing that makes it extra interesting for me personally is that they're using a VE, they're using a variational autoencoder.
Right.
And that's super important because that means that you can take any sample you want and push it into the latent space.
Right.
And with a lot of generative models, you can draw samples from latent space, but you can't take a particular image and find its location in latent space, or you can try to, but you can try to find a similar position in latent space, but it doesn't work super well. Whereas in this case, yes, you can, and I'd love to induce that latent space using a large unlabeled data set, which is something that's very feasible for me to get. And then try training on those. Training that latent space would be interesting. and you can always fine tune the encoder after that as well.
Mm-hmm.
That would be feasible. That sounds pretty interesting. You know what? You've been doing some pretty interesting work on data augmentation. I suspect you might be looking at things like using GANs to do data augmentation.
Yeah, that's what led me to the VQ-VAE2 paper, because Vinyals had also published a paper where he's doing data augmentation from the big GAN samples and finding that it doesn't work really. It gives him like a 3% relative improvement at like 1.5 times the compute cost. But then he says that these VQ-VAE, they actually do a little better than the GAN-based augmentation. So that's what led me to, because I've been so focused on GANs, I never really got into variational autoencoders as much, but now that they're starting to surpass it on the data augmentation thing, I've been more interested on it. And that paper is, I think it's an ICLR paper that I'll send to you after we talk.
Yeah, I assume you're going to put all these papers in the show notes, right? We've talked about a few papers.
Mm-hmm.
I'll have to send you some links. Model distillation, that by itself is a pretty important topic.
Right.
That there's been a few papers in that have been not just doing good science, but are also like very, very readable, and they lead in a couple of kind of unexpected directions. So model distillation can give you a smaller model, but also it can let you copy somebody. If somebody has a machine learning as a service where you put in a sample and they give you back class probabilities, you can copy the model very easily, and that's something people should be aware of when they design those services. I did a little article with a couple of friends on that works really well. But there are some other things, like for example, with some very large models we want to train in a distributed setting, right? But it gets really expensive to pass the weight updates around between your nodes in your cluster, if you're lucky enough to have a cluster. These poor people, how do I pass all these updates around my 1,000-node cluster? It's such a pain. I'm so sorry for you. What problems you have? But there's a way around that using model distillation, which is that instead of passing weight updates, right? So the idea is that you're training clones of a model on the same data set, on different shards of the same data set on a huge cluster, and you share out these weight updates, you average the weight updates, and then you gradually, you're able to use all this computational power that you have. Mm-hmm. But as you scale up your cluster, you start to lose the computational benefits because your network bandwidth is just getting choked, right? All these weight updates, you're spending too long waiting for the weight updates. And they're big, right? Because every node has a full copy of the model, so every node has new information about every parameter. And even if you cut it down to the parameters change a lot, every node still wants to send important messages about 10% of its parameters. And if you cut it down, at some point, if you cut it down to just a few parameters from each one, not much information is moving. So there is a paper about model distillation where the authors say, right, instead of sharing parameter updates, what we're doing is we are sharing model outputs for a given common sample, right? Mm-hmm. So it's like you're on a college course and you say, hey, I'm working with this assignment. These are the kind of results I'm getting. Do those line up with your results? And I say, well, in most cases, yes, but in this question, I'm getting very different numbers. And basically, what you do is you basically augment the loss function. So you're trained using let's say your normal cross entropy, but you add in an extra term, which is I should try to minimize cross entropy, but I should also try to make sure that my answers are somewhat similar to the answers of my peers.
Yeah, really interesting.
So now instead of having to share, weights, updates to weights all around the network, you're sharing your opinions of what the class vectors are on some smallish batch, and that's just a lot less data, and that lets you scale up to. That lets you then get benefit from using much larger clusters. Gone way off SWA there. On distillation, I feel it's a topic that people are possibly less aware of than they should be.
Yeah, really interesting. But, thank you so much for doing this and for starting the first episode of the podcast. I really hope that the production quality on this first episode comes out all right.